Let's consider now momentum conservation and derive from that what is known as a Navier-Stokes equation. If we use now the conserved quantity to be the momentum and apply that to the conservation equation, then this is the equation that we get. Now let's expand here this gradient and this V, this A and this gradient here in component form. So that's our equation now. Remember that the indices here are repeated, J here and J. Now first, let's substitute Nm by the density. And this fourth term here, the derivative of Vi with respect to Vj, is a Kronecker delta, because it's 1 only when I equal J and 0 otherwise. So we're going to have a Kronecker delta of Ij, which then contracts with the Aj, leaving only Ai. If we substitute now the average of V for the mean flow, where we still have this term here, which includes the random velocity. Keep in mind that we're using a decomposition where the particle velocity is the mean flow plus a random velocity W, and the average of this W is 0. So how do we deal with this term here that has the average of Vi times Vj? We can find this tensor, big P, which is a density times the average of the fluctuations. So W is a residual velocity relative to the bulk flow. Now, if we substitute W here by V minus U, then we redefine P as, and distributing it, then we have these 4 terms, which is combining bulk flows U, which are mean velocities, with the velocity V, which is the total velocity with the random one. Now, the U is a mean velocity, so the angle brackets do not operate in it. It only gives the same quantity. So we can replace this by, and now the average of V is U. So substituting the averages of V by U, what we have then is this expression then for the tensor P. We use this then to replace this as an expression for rho times the average of Vi Vj. Isolate this term. So this is very interesting. We have that the average of Vi Vj, the particle velocities, is an average of the bulk flows plus this tensor P. As we're going to see, this tensor P is a pressure. So the velocity of the particles, it makes sense. It leads to a bulk flow plus a pressure. And the pressure comes from the random motions. If we substitute this expression back into the original equation, we find the Navier-Stokes equation. This is known as the conservation form of the equation, because what you have here is the quantity, the momentum, the flux of this quantity, and then on the right-hand side, you have the sources and sinks, the pressure and the body force. You can see that the mass continuity equation is written in the same way. You have the quantity and the flux of this quantity, and in this case, in the mass continuity, you don't have any source or sink. That's why this equation in hydrodynamics is called continuity equation. The continuity equation appears in many places, but in hydrodynamics, because mass doesn't have a sink or source, the equation for the density becomes identical to the continuity equation. You're going to see that referred to as only the continuity equation, or sometimes called the mass continuity equation. And in the same way that we could cast the mass continuity equation from conservation form into an advection equation, we can do the same thing for the Navier-Stokes. Let's see how that happens. We can cast the equation in advection form by expanding the first term. Use the product rule here and expand this. So you have these 2 terms here, rho times the derivative of U plus U times the derivative of rho. And now we use the continuity equation to remove the derivative of the density. So going back to the mass continuity equation, we're going to substitute the rho dt by the divergence of the mass flux rho u. So here we made the substitution. And now we expanded the third term. You see here that you have rho uj and ui. If we use the product rule, separating ui from rho uj, we're going to see that it's going to produce a term that is going to cancel with the term that came from the continuity equation, leaving us with this equation. Now, if we divide all the terms by rho, that's what you end up with. So you already see here, you have the time derivative of the velocity. This is an advection term. Remember that the j here is repeated, so it sums. So this is a u nabla term of the I component of the momentum, which is the same thing that is being advanced in time. And then here you have the the pressure term, and the body force, the acceleration, the external acceleration. We can go a little further. We can decompose the tensor P into its diagonal term, which is little p, the pressure, and a traceless component. We're going to use a negative sign here for reasons that are going to become clear later. You decompose the tensor Pij into the pressure, that is a diagonal term, and this other component. The diagonal term is the pressure, and the off-diagonal terms is a shear. As you're going to see, it's going to give us a viscous force. Given how we defined the tensor big P, then the pressure, which was by this expression, then the pressure is the diagonal term, so it's going to be W squared. And because there are 3 components, then we're going to divide that by 3. That leads us to this expression for the pressure. So substituting this back in the original equation, we find the expression for the tensor pi. And this tensor is the viscous stress tensor. The Navier-Stokes equation that can be written in this form is the same equation that we had up here. This is written in component form. So we have here the advection term, u dot nabla of u. We decompose now the tensor P into the diagonal form, that's the pressure, and the viscous force. And you have here also the body force, the acceleration due to external forces. This body force can be gravity, can be the Lorentz force, any force that is acting on the material. Again, this is written in terms of the quantity, the advection of the quantity, and the source terms. The source terms in this case, the pressure, the body force, and the viscous force.